Okay, so it's great pleasure to have Baris Coskunuzer from University of Texas, Dallas. So he's going to tell us about filling values and persistent homology.
Okay, thank you very much for the invitation. So I'm gonna talk about, okay, got it. So I'm gonna talk about two very important notions. One of them is from metric geometry, the other one from applied algebraic topology. And I'm gonna try to make some connections between them. So this is a joint work with Alexey Balinsky and Facundo Memoli. This is a work in progress. I am just gonna try to promote some of our results. There are others as well, but since we have only 1 hour, I'm just gonna try to give some pictures for you to express both of them, and I wanna show the relation between them. Okay. Yeah. Okay. So we want to bridge metric geometry and applied algebraic topology. So there are several notions from both sides try to measure the size of a manifold. So metric geometry is basically try to measure the size of a manifold by definition, but persistent homology somehow is computational way to gives you a computational way to compute the size of given homology classes, and they are it turns out they are closely related. Oops. Okay. Okay. So today I'm just going to focus on persistent homology is there are you can discuss this in very different settings, point cloud setting, graph setting, or image setting. I'm going to focus on only one setting today. So if you are interested in other settings and applications, come to afternoon talk. So I'm going to give you lots of applications about this, but this talk is only about the point cloud setting. I have a point cloud, like finite set of points in Rn. But you can generalize everything here to compact subsets in norm spaces too. But I am just going to focus on finite point cloud in Rn. And so the basic idea about persistent homology is you give me some data or point cloud or something like that. I'll give you a sequence of topological spaces, and persistent homology basically keep track of the topological changes. I'm going to give you an explicit example in a minute. For homology computations, so I'll give you an example here. So the continuous spaces. So the most basic one is, I mean, we are going to see in a minute, our neighbors of the point cloud is a very natural filtration here, but for computational purposes, you want to get some combinatorial objects, a simplicial complex, and most natural ones are variatory strips and Czech complex. And today I'm going to focus on only these two. But you can also use alpha complex and other stuff, but to keep it simple, I am going to only focus on variatory strips complex and Czech complexes coming from point clouds today. Okay. Czech complexes. So Czech complexes, let me show you a picture. This is going to be better. So if two balls intersect each other, then I'm going to put an edge between them. So the centers are there. So x1, x2, xn are my point cloud. I am looking at the R balls of them, and they are intersections of them. Okay. Now, Czech complexes obtained by if two R balls intersect each other, then put an edge between them. If three balls at the same time have a non-trivial intersection, then I put a triangle between them. If four balls, when they intersect, have a non-trivial intersection, 1 point in all of them, then I'm going to put a tetrahedron between them. This is called Czech complex. Very naturally, for any R, you give me a point cloud for any R, you can construct this. Just look at the R balls. If they intersect, you put an edge between them, etc. This is called Czech complex. So any R neighborhood of your point cloud, I give you a simplicial complex like this. And it's going to be very important for us. Variatory strips complexes are a little bit different, and most applications use viatory ellipse complexes. I'm going to explain why. Here, it's very similar. Again, I have a point cloud. I'm looking at R balls. If these two guys intersect each other, if these two guys has distance less than R, then I'm going to put an H between them. And if three guys pairwise distance is less than R, then I'm going to put H between them. So you can tell me it's the same thing with Czech complexes. That's not, because in that one, I am always in Czech complexes, I always depend on the ambient space. If you look at this picture, these three guys, so geometry of the ambient space is very important. I have three R balls, so they can intersect each other pairwise, but they may not have a non-trivial intersection right here, depending on the space. For example, if you have a negative curvature or positive curvature, it all changes. So viatory ellipse complexes are better choice most of the time because you don't depend on the ambient space. You just need to know pairwise distances of points to construct this. So if you know all pairwise distances, then you can immediately give me which edges I have. If I have a complete graph, subgraph, then I'm going to fill this guy with triangle or tetrahedron. That's it. This is what viatory ellipse complexes. So they are very closely related, but Czech complexes are geometrically more natural because it is because of the following result. Neuer theorem tells you I am basically, as a geometer, I am mostly interested on these R balls. R balls are more, so I give you a point cloud, I give you a filtration coming from the R balls of my point cloud. And it is homotopy equivalent to the Czech complex corresponding. Not viatory ellipse complex, but Czech complex. They are different. But yeah. So let me show you the example here. So let's look at this. I hope this is Czech. So this is a point cloud. I am increasing my radius. This is my R balls, 1 balls, 2 balls, 3 balls. But here, when you look at here, I am constructing, I am putting H between them. This is the corresponding Czech complex. Let's check if they are homotopy equivalent. So these are balls, they shrink to a point. These guys are okay. I have one loop here. This is homotopy type of a circle. Yes, that's fine. So Neuer theorem tells me when the blue space and the black simplicial complex are homotopy equivalent all the time, no matter what. When you increase this, like, oops. Okay, maybe I should use. When you go one by one, you add edges and triangles, etc., and you get to here. And there is a relation between them, like this. Here you can see any. This is also a very straightforward calculation. For Czech complexes, so these are all coming from R balls. The corresponding Czech complex for R is always inside 2R viatory ellipse complex, and it's always inside root 2R Czech complex by definition in Rn. So Rn is important here. Remember, Czech complexes are very dependent on the ambient space. That's why. Okay, persistent homology is coming for, let's discuss that. So this is the technical definition. I'm going to skip this. I'm going to show you. Yeah.
You were saying it's very dependent on the ambient space.
Yeah.
Is there a version with different coefficients for, say,
not about the coefficient. It's about the geometry, basically. So viatory ellipse complexes, it's very easy. If the distance between the points, I put an H, etc. But
I meant this statement that Czech complexes contain in course.
Yeah.
Like
it depends on the Rn. Yeah.
So this like root 2, do you get a different coefficient?
Yes.
Like a general
Yes.
interval?
Yeah.
But there are statements nodes.
I don't know. I've seen some statements, but we are going to come to this point when the space is hyperconvex. When it's hyperconvex, they are same. Czech complexes and viatory ellipse complexes are going to be same, and we are going to use that. Okay. So let me give you a crash course about the persistent diagram, the persistent homology. So I am pretty sure everyone knows it very well, but let me go over this again. So this is a point cloud in Rn. Basically, TDA is trying to extract some important information about the topological features. Topological features you see here. For example, in here, I have a point cloud, but implicitly, I can see there are two loops here. The silhouette of two loops, I want to extract this information. The way the persistent homology works is, okay, so let's, so when you look at from the, very far away from this point cloud, you cannot distinguish these 2 points. When you look at farther away, you cannot distinguish these 2 points. This is the main idea here, to get this two-circle impression out of this. And instead of that, we are going to cheat. We are going to look at the R balls. So when I increase my R balls, this is like looking at from far away, because these two guys are very close to each other. But for small r, they are just merging to each other. That's the impression we are going to have, and this is going to mathematically formulate this. So I am increasing radius here. For 0.1, 0.2, 0.3, I am increasing here. So I have 15 components here. So I am starting 15 red bars. Red means 0-dimensional. I have 15 components. And when I get to 0.5, I see 1, 2, 3, 4, and 5 components. That means along the way, they merge. And I now have only 5 components left. The other ones are died. So some of them died at 0.3, merged to other guys. And then 0.4 and 0.5, there are only 5 components left. There are 5 pieces. This is the 0 barcode. In here, when I continue here, after 0.7, everything gets connected. I am increasing the radius of the balls. And then at 0.7, it becomes one piece. It becomes one component. And that means everything gets connected. After 0.7, I have only one bar continuing forever. It doesn't go anywhere. It will be there. So this is the barcode for 0 dimension. Those are the bars corresponding to these components from this point cloud. Blue ones represent the loops, one-dimensional topological features. I am talking about one-dimensional homology. What I do here is, here there is no loop, you can see, 0.5, but when you get to 0.7, this first large loop emerge. I am going to start a loop here. There is a hole here, one-dimensional homology. And 0.9, the second loop emerge. And I continue here. When I get to 1.5, this second loop, no more non-trivial homology class. It became trivial. And I am going to say it died at 1.3. But this is still surviving. There is still a hole here. And finally, the other one is going to die at 2.5. This is going to be my persistent barcode. Red ones represents zero-dimensional features. Blue ones represent one-dimensional features. This is the barcode, and this is the persistent diagram. It has the same information, initial point and end point. You can see it here, 0.7 to 2.5. I am marking them as persistent diagram. They are the same thing. Okay, this is the persistent homology. Now I'm going to confuse you just a little bit, because there is a, okay. So what I told you is about, I am lying here because the whole structure comes from a very deep interval decomposition theorem, the modules stuff, and it's very algebraic. So you have basically here, you have a sequence of vector spaces with the injection maps, and it will give you some persistent module you can decompose into barcodes. And persistent barcode basically corresponds to the every interval. So you are decomposing in the intervals here. So, but this is the algebraic definition. It doesn't directly match what I told you. What I told you, something starts and then some topological feature starts. This is let's say topological definition of the persistent homology. And then when it becomes trivial, it dies. And it turns out this guys sometimes does not match. This is a very technical point, but I am always going to work with homological persistence, let's say. The topological definition I told you. But the persistent diagrams always captures this information with small modification, but it does not increase the homological lifespans. It always decreases here. So there's slight difference here. I am not going to spend time on that, but you can keep the definition I give you. In this filtration, the first time my topological feature appears is going to be my birth time. And the last time it appears in my filtration, it becomes trivial, is going to be my death time. This is the definition I'm going to use. They don't match. There is a technical problem here, but we won't use that. So it's always true that homological persistence, the topological definition I gave you, is always greater than, lifespan is always greater than the algebraic one. So I am going to always bound these guys. It automatically implies here. Okay? Yeah. Okay, that's a good question. Now, persistent diagram. So let me give you a very simple example. You know the elder rule. So okay. So you have two guys, two topological features going to they are not homologous, but after some of guys die, they become homologous. They don't die, but they become homologous. So this guy merge here. So imagine you have two loops. They are not homologous in the original space. Okay, and then but when you go further in your filtration, they become homologous, but none of them died. They are still non-trivial, but none of them is. But in my homological persistence, when both of them died, it's going to be my dead time. You can merge to the other guy without dying, and that's going to kill your barcode. So your bar should continue if you reach your trivial time, but if you merge the other guy along the way, you disappear, but you are not trivial yet. That's the problem. But unique decomposition exactly tells to this merging. So that time for this guys. But for my definition, when the loop becomes trivial, indeed, in the whole filtration, it's going to be my dead time. They are not the same. So there is a okay. So Berat's paper. So they have this example. Facundo, Berat, and Lin. They have this explicit example. Lim, Memoli, Okutan, 2022, I guess. There is their paper. They have exactly an example about this. They don't match. Explicit example.
Why would you not do that something is not that?
No, I mean, because
the examples you have, all these zero homology functions,
yeah. No, I am talking about, yeah, you are right in that perspective. I'm always talking about the higher one. Zero dimension is always nightmare for us because of lots of exceptions. Here, what I am trying to tell, I can geometrically see this. That's why all my bounds about this guys and this guy always supersedes this guy. So this is coming from persistence diagrams. This is coming from the homological persistence. And since I'm going to use geometry, I want to play with this guy, which I can control. I can, so because the first time it appears in my filtration and it becomes trivial, I can understand them. But merging stuff is much more complicated for me. Okay, yeah. So I'm going to define two types of filling radius. Filling radius is a very important notion in metric geometry. The extrinsic one is very easy to understand. So I give you like in Rn, in somewhere in ambient space, let's say in Rn, I give you some k-dimensional manifold, closed manifold. So K homology is non-oriented, let's say oriented. If non-oriented, I'm going to use ZT coefficients, etc. Let's say I have k-dimensional manifold in Rn. the k-dimensional homology is non-trivial because it's a closed manifold. And my question is, okay, this guy is non-trivial. So what is the first time it becomes homologically trivial in the R neighborhood? So I am increasing R neighborhoods. Let me give you this example. So for example, this is your ellipse. Okay, let's look at the R neighbors of this guy. Okay, is this trivial in this guy? No, it's still non-trivial. And let me increase my radius just a little bit. Let's say this is, and let's say this is x squared over 16 and y squared over 4 is equal to 1. Let's say this is y squared over 1. No, 1 is not enough. Let's say 9. This is n1 and 0.5 and 0.7. I am still increasing just a little bit. You see here. It is still non-trivial. You can see it here. And you go further. And when you hit 1, you see here, it gets filled. Because this is plus or minus 1. And then one neighborhood becomes trivial. The first time it becomes trivial is my filling radius, but extrinsic filling radius. That means I am taking the neighbors in my Rn. That's going to be crucial. I have a manifold and I have an ambient space. I am taking R neighbors in my Rn, and the first time it becomes trivial, which is this guy, M is null homologous in an Rm, the smallest one. R is increasing. The first time it becomes trivial is going to be my extrinsic filling radius. The extrinsic word comes from, it depends on the ambient space. This guy depends on the ambient space Rn. But the Gromov's filling radius, well, this is the ellipsoid, for example. In the ellipsoid, you can see it here, all neighborhoods, and then the filling radius of this guy will be the smallest axis, which is 3. When you hit 3, it will get filled. This, you have a solid ellipsoid, and then it becomes trivial. Okay? And Gromov's filling radius, this is the more important and famous one in metric geometry. It doesn't have an ambient space. You give me any Riemann manifold with a metric. There is no dependency in the ambient space because there is no ambient space. I just give you a manifold. And for that manifold, there is a filling radius definition in the following space, following way. So it tells you the smallest, exactly like the extrinsic filling radius, but I have one condition for the ambient space. Distance preserving maps. So that means following. You give me any manifold M, okay, and you embed this to somewhere else to talk about this filling radius. So I'm going to take neighborhoods in here, but I have a condition here, distance preserving. So any 2 point here must have the same distance in here. This is distance preserving. And look at the R balls and Rm inside Y, and smallest R is going to be its filling radius for Y. And for all such manifolds, take the infimum. For all such distance preserving embedding, take the infimum. This is Gromov's filling radius. And there is no dependency in the ambient space. You give me a metric, I am looking at all ambient spaces, I am taking the minimum of them. This is going to be Gromov's filling radius. This is a very famous metric invariant for a given Riemann manifold. And for this guy, now my extrinsic filling radius is 3 because I am taking my neighbors in Rn. It's going to be 3. So what's your guess for the Gromov filling radius? For the flying saucers for this picture. Is it going to be 3 again? Is this okay? I am inducing a metric for this guy from Rn. Now, is this embedding distance preserving? What do you think? So the distance of this point to other point is equal to 6 or 20 or somewhere 20. So if I don't refer to the ambient space for my space, the distance between these 2 points will be about 20. But if I embed this to Rn like this, it is radically reduce the distance between these 2 points. So this embedding is not a legit embedding for Gromov's filling radius. So you cannot use this space for this guy. So it turns out for the same guy, Gromov's filling radius is going to be about not 100. It's going to be about 10. It's going to be about 10, but the extrinsic filling radius is going to be 3. Now, I want to make a comment here. Gromov's in his this is 1983 paper. In that paper, he showed that no matter which space you take, there is always a best space for Y, which is Krotowski embedding. Krotowski embedding is this. For any space, any metric space, X, and infinity X is space of functions from X to R. Okay? And you use supremum norm. And Krotowski embedding is exactly sent X to L infinity X. Can you see my marker? Do I change it? Yeah, here. L infinity X in the following way. X goes to this function. Any X here goes to the function from X to R. So Y goes to the XY. And this is an isometric distance preserving embedding. And this is the best one always you can get. So no matter what, Krotowski embedding will beat all other embeddings. So you can say Gromov's filling radius is the same thing with extrinsic filling radius in L infinity X. It's the same thing. Yeah, the R becomes the smallest one. Yes, exactly. Yeah, you can, because I mean you can choose very different ambient space with distance preserving way. But in that sense, for example, if your ambient space is something like this, and your origin space is this, you see, to fill this guy, you have to go a lot of. So this paraboloid is my original space, Y. This is going to be my X. And let's say this is distance preserving embedding. Look at the R neighbors of this. It's always, when you take this very long, unnecessarily you are going too far. But in Krotowski embedding, you always achieve the minimum here. You mean the manifold becomes null homologous or cover? Yeah. Yes, exactly. Krotowski embedding achieves that. Yeah. Yeah. So Krotowski embedding is an infinite dimensional space, but you have an isometric copy of that. And the neighbors in this infinite dimensional space will give you the smallest R for this. So this infimum achieves it for Y Krotowski embedding. Yeah. Okay. So the extrinsic and intrinsic filling radius are completely two different notions. They are related like this, but they are not directly. Now, when I talk about point clouds in Rn, which one is more relevant to my context? If I'm talking about persistent homology. Okay, this is my question. I have a point cloud in Rn. I am constructing my persistent homology, Čech complex or Viatoris-Rips complexes. And you see that there is a relation between this filling radius and the persistent homology because it becomes trivial at some time. But which one is more relevant? It turns out extrinsic filling radius is more relevant because you already have the ambient space. You construct your guys in that space. And then if you fill that in this ambient space, then your homological features becomes trivial. This is, but Gromov's filling radius, it turns out, will be important for Viatoris-Rips complexes. Čech complexes are related with the extrinsic filling radius, but Viatoris-Rips complexes will be about Gromov's filling radius. Okay, so again, in the same paper, Lim Memoli Okutan, they showed that if you give me any Riemann manifold, not ambient space, a closed Riemann manifold with a metric, then if you look at the Viatoris-Rips filtration, and again, if you give me the metric information, I don't need a ambient space for Viatoris-Rips. All I need is pairwise distances, so I can construct my Viatoris-Rips filtration. And they showed that the persistent diagram so gives you for the fundamental class, you get this guy, 2 rho m. The lifespan of the fundamental class, the whole manifold, is exactly twice the Gromov's filling radius. No, this is a manifold. So immediately becomes infinite dimension. This is not a finite point cloud. So you give me, for example, a torus. This is your point cloud, the whole torus. Okay? And then it immediately becomes infinite dimension. The Viatoris-Rips complex. But again, in the Viatoris-Rips complex, this is still non-trivial. You are increasing, and hit somewhere. And it turns out the Gromov's filling radius, twice the Gromov's filling radius, this is the dead time for your guy. Basically, they say 0 to rho m is exactly your PDN. M is an N manifold, and N persistent diagram for Viatoris-Rips filtration must have this bar. This is their result. It is coming from, again, just the metric information. There is no ambient space here. I can use Viatoris-Rips because all I need pairwise distances. Okay. So now, Čech persistence and intrinsic filling radius. When you look at here, remember my flying saucer example, this example, the dead time with the Čech persistence, you can see that the dead time is, if it starts at 0 birth time, it dies at 3, the smallest principal axis. Because when you look at the R neighbors in Rn, R3, for example, and at 3, it becomes filled, and then you are done. For Čech persistence, Gromov filling radius is highly overestimates, because you can see it here for the same example. It is not 100, it's 10, but you can make it very large by making the other guys very large. But the Čech lifespan is 3. Now, filling radius of a homology class. Now, I'm going to make a definition, very natural definition. So, in the filtration, let's say in the persistent diagram, you see a topological feature. In the birth time, look at all the representatives. The smallest filling radius of this representative is going to be the filling radius of the homology class. In this filtration, in this NRX, I have a sequence of balls and increasing. I see it homology class somewhere the first time. At the birth time of this homology class, I am looking at all the K cycles. And then smallest filling radius will be exactly the filling radius of the homology class. This is the definition I am using. And it turns out the Čech persistence, basically by definition, This is how I define it. When this S is becoming trivial, the whole homology class immediately becomes trivial by definition, because Čech persistence by Nerve lemma are both and the Čech simplicial complex are homotopy equivalent. Whenever a homology class becomes trivial in R balls, then it will become trivial in the Čech complexes. And by definition of this, it becomes less than or equal to. Now, good question here. They must be same or not. Unfortunately, the way I define this, they are not same. For example, for a circle of radius 1, the Čech lifespan is just 1. Imagine this, a very simple example. Let's say this is S1 in R2. Okay. And you increase the balls. This is the 0.1, 0.2, etc. And when you hit 1, it becomes trivial. The Čech persistence for this guy is going to be 1. So 0, 1 is your PD1 S1 in R2. You will get the R. So this guy, let's use red, is your original space S1. This is your original space. You look at R neighbors of this. When this becomes trivial, when R is equal to 1, it becomes the whole disk. Then the lifespan of this circle is going to be 1. Now, I'm going to take the same space, but I am just going to add one point in the center. This is my X. Okay? For this guy, this becomes a homological immediately, the circle. And look at the R neighbors of this guy. Now, 0.1 neighbors of this guy here, here, but I also have something in here. And then because of this point. Now, it becomes trivial in the neighbors of the homological, neighbors of the point cloud, but here I am only taking care of, looking at the neighbors of the original homology class. I am not looking at the contribution from the other points. That's why it's less than or equal to here. It's not, it cannot be equal to, here it's going to be 0.5. If you think about that, the lifespan of this homology class will be 0.5, because when you hit 0.5, there is a contribution from the middle, and then it will close the whole space. So in this one, 0.5 is my lifespan, but the filling radius is going to be still 1 in this one. Okay? Now, how much time do I have? Am I going slow?
20 minutes, so it will be 1 hour.
Okay, okay. I need to speed up. I need to... What?
Doesn't this make the filling radius
Uh-huh.
bad invariant?
No, filling radius is about the Riemann manifolds. Oh, okay.
So it doesn't say anything about the cycle.
Okay, yeah.
Why is
Yeah.
it defined?
Yeah, I know I am confusing you. So the Gromov filling radius is always about a one closed band. But when we talk about persistent homology, we have a sequence of filtrations, lots of homology classes appearing in here. So this is coming from the interaction. So Gromov filling radius only focus on one manifold. But we are trying to relate them. So if something appears in the filtration, let me look at the filling radius of that guy from geometric side, and then let me relate them. But originally, I have only one manifold for Gromov filling. That's a very good invariant to measure the size of a manifold, because I give you a very abstract manifold, some like n-dimensional sphere, etc., some n-dimensional manifold with some Riemann metric. Is this Riemann metric indeed tells me it's a large manifold in some sense? Uh-huh. Yeah. because of the point cloud. So I am looking at the filling radius in the point cloud setting. But originally, there is no point cloud. There is only the cycle. Yeah. Exactly. Just one point can change everything here. Yeah. Urysohn width is another metric invariant, which is very nice in the sense that it tells you essentially what is your dimension. So, for example, if you look at this torus, very thin torus, it is a two manifold, it's a torus, but it's essentially one-dimensional. It's just like a circle, but it's living very close to the circle. I can give you like 50-dimensional manifold, but it might be a very close to like a 7-dimensional manifold. Its basic dimension is 7. So Urysohn defined this very nice notion called Urysohn width to make this understanding more formal. So what he did is, I am here. Okay. So this is the definition of Urysohn width, and there is a K here which is very crucial. So what he does is, let me give you one simple example to understand what's going on. Urysohn width basically does the following. So you give me n manifold, let's say 2 manifold. And then I'm going to plug, I'm going to find, so I'm going to talk about one Urysohn width of this manifold. S, let's call this S. I'm going to find a one-dimensional something. This is simplicial complex. This is simplicial complex I want to take. And let's take, so this is the map from S to this simplicial complex K. Okay? And let's look at the preimage of every point. So these are the points we are talking about, etc. And then he says this largest, so you look at all such red simplicial one-dimensional objects. Look at the fibers, look at the preimages, and the largest one will be your, by minimizing about all red simplicial complexes. The large, so for example, if the largest guy is this, and the red one is the minimizer of this, the Urysohn width of that guy, the diameter of the circle. Total diameter means farthest 2 points of the set. Yeah, there are lots of one. For example, you can take this one too. And when you take this guy, when you project there, you'll get a much larger guys. So same guy. I'm going to take another example. And let's look at this guy, for example, very trivial. My guys will be something like this. You see? They are not so small. In this one, much smaller. And if this width is very small, K width, then I'm going to call that manifold essentially K dimensional. So, for example, 0 width means we are taking 1 point, for example, and it's going to be the whole diameter of the manifold. And this is a monotone decreasing sequence because of the construction, and you can achieve that in here. So this is Urysohn width, and Gromov also in the same paper showed that Gromov's filling radius is always smaller than n-1. Urysohn width or half of it. And since I don't have time, let me give you a glimpse of the proof here. So we relate Viator's series persistence exactly with Urysohn width by using this result. It turns out this is a very nice exercise, let's say. Virtual strips processes is always very ugly to talk with. In Czech processes, you can use geometry. You can go to our neighbors, etc. No lemma. But virtual strips processes, you don't have anything. But what you can do, you can cheat here. You can carry everything to the Krotowski space, and it becomes Czech persistence in Krotowski space. When you do that, in the Krotowski space, the virtual strips persistence is exactly the same with the Czech persistence. Why? Because Krotowski space is hyperconvex. Whenever two, so if you have like 7 points, if they are all they are all pairwise distance is smaller than 5, then their 5 balls must have a non-trivial intersection altogether. This means hyperconvex. In Rn, you don't have this property, but in an infinity X, Krotowski space, you have this property. That means whenever you have a Czech complex, it must be the same thing with the virtual strips complex with this coefficient 2. So, and you can exactly use similar ideas, because this time here, my Gromov's filling radius is this guy. Exactly my extrinsic filling radius in this space. And I can bound extrinsic filling radius and the Czech lifespan. You can use these arguments to prove this inequality. This is my viatory strips filtration persistence, and it comes from the Urysohn bit here. Okay. Let me finish with one interesting observation. You can think of this as a very simple observation, but it's potentially very useful. Yeah. Yeah, always point cloud. Okay, so this is a point cloud in Rn. Now I am looking at viatory strips filtration. The pairwise distances of the, so when I get my pairwise distances, I throw my Rn away. I am not using Rn. I just need the pairwise distances. After that, it's everything viatory strips, but the viatory strips filtration is exactly the same thing with Czech filtration and in Krotowski space. Yeah, in viatory strips filtration. Yeah. So, okay. Yeah, no problem. So, viatory strips filtration, for when you increase your R, you get enlarging simplicial complexes. And there is non-trivial homology classes. W is one of them. For that guy, now, I don't have any reference to Rn now. I just have these simplicial complexes you give me from viatory strips. That's not the Czech complex anymore. That's the viatory strips complex, and there are homology classes there. And for any of them, I have this inequality. And this is for the whole space. X. And R, okay. No. No. Yeah, you are right. That's gonna be okay. Where did I miss here? This is going to be okay. UWK minus 1 and BWX. Is that right? I need to check that. No, X is point cloud. Urysohn width of that guy. No, you can still define Urysohn width just as before, but there must be something like this in that definition. Let me check. Did I mess it up here? Yeah, I need to fix that. Yeah, I'm not sure it's NBWX, but you are right. There is something else here, not just X. No, I mean, there must, so yeah, I am relating these two guys, but there is something else here. Okay. Yeah, I'll fix that. Yeah. Thanks for catching this. Okay. Do I have time or I am done?
8 minutes, but you can, I mean, to get the full 1 hour.
Okay, yeah.
It's okay.
Okay, yeah. Principal component analysis is basically you give me a point cloud. It looks at the best fitting ellipsoid in the sense that your distances are minimized to this ellipsoid, L2 distances. So, for example, you have a point cloud like this, and then the best ellipsoid fitting here, maybe I should draw like this. The best ellipsoid in L2 distance, minimizing the L2 distances to this ellipsoid, is going to be your PCA, original PCA, principal component analysis, but L2 distances. Now, PCA infinity, this is what we defined. Basically, what we do is, instead of L2 distances, we are now looking at the L infinity distances, which means if you give me a point cloud, I am going to look at the smallest ellipsoid in any direction. I don't know. Smallest ellipsoid, it contains the point cloud. The L2 optimization does not necessarily tell you that it must contain, but L infinity one will tell you it must contain. And for that, here, so we define a smallest ellipsoid containing my point cloud. Okay. Now, for any, okay, so the main idea here is, if you give me, so imagine this. These are your, you have a point cloud. And this is your smallest ellipsoid. You have two axes here. This is my first principal axis. This is my second principal axis containing my point cloud. What I do here is basically when you have a homology class in the point class, some neighborhoods here, the check complexes, then it must get non-homologous. So that it basically tells you the large span of anything cannot pass this guy. So imagine the following. You have in this point cloud filtration creating a homology class, like one homology class, two homology class, whatever it is. But whatever homology class you take, when you take R neighborhoods, when you pass this threshold, it must get filled. This is what we are trying to achieve here. Because it tells you the whole ellipsoid will be get filled, and then your homology class will get filled here. And by using this, we have a very nice result. So let me quickly tell you about this. This is Cech stability theorem. This is bottleneck distance between two persistent diagrams. It's always smaller than the Hausdorff distance in the ambient space. And viatory strip stability theorem. This time there is no ambient space. You have Gromov Hausdorff distance between two spaces, and you have a two coefficient here. This is the, exactly the viatory strips coming from viatory strips filtration of two different point clouds. Now, by using this two stability theorem, now take any point cloud and project down to the k-dimensional subspace. And then your k-dimensional subspace will live in Rk. There is no K homology there. There cannot be any K homology. It will be crushed. In Rk, in R3, there is no 3 homology. You cannot have a 3 closed manifold in R3. By using this simple argument, you can show that by using the stability theorem, okay, X can be a very complicated space, point cloud. You just look at like K-dimensional projection here and look at the persistent diagrams of those guys. This is much easier to compute, for example, in K-dimensional space. And it turns out the difference between these two guys cannot be large, bottleneck distance cannot be greater than the length of this axis here. This is basically some sort of dimension reduction for persistent homology. Yeah, it can be. If you have outliers, this is terrible. For example, in original PCA, outliers is not a problem, but for ours, outliers is a problem. If you have like very good ellipsoid, but if you put 3 points somewhere, then you are done. Unfortunately. Okay. So basically, so we are trying to bridge these two fields with these arguments. There are lots of nice. We believe that we just scratched the surface. There are lots of nice interaction between these two fields. In metric geometry, there are lots of invariants, which is very hard to compute, but Peirce's homology can give a way to get some lower bounds for them by using these ideas. And in the other side, metric geometry has a very nice invariants to measure the size of a manifold. Those can be very efficient to give some idea how to some very technical terms for Peirce's homology too. So I'll stop here. Yeah, thank you.